Well, hello, everyone. This is Noah Shartoff and John McNally back with you again. Today, we are going to be talking about a few features of Wolfram technology that can provide some extra help. Of course, the nature of any tool is to provide extra help, but these features are ones that take an input and then make some suggestions about what else you could be doing to understand the thing that you're studying better. As always, we'll be answering questions live, so feel free to type any into either the YouTube or the Twitch program that you're viewing this on, and we will get to them as possible. And without any further ado, let's get into step by step and beyond. So Wolfram technology, we're all about answering questions. But sometimes the interesting thing is not just what the answer is, but why. So we'll be going into some features of the technology that can help you see that. Specifically, things to know how you know that the answer is right, like step-by-step solutions. Things related to the question that could be interesting, like related computations and full Wolfram alpha results, and what else we could explore related to the answer, like the suggestions bar. Now, I'm working today in Wolfram Alpha Notebook Edition because it's a Wolfram product that's specifically designed to give extra help when we think it could be useful. But most of these features are in Mathematica. We'll be going into a little bit of that detail further on. But for now, let's get started with some examples. So here's integrate x squared times cosine of x. Those of you who have studied calculus will know that this is a doable but annoying integral. And you could just put that into the program in natural language. It'll translate it into code. It'll give you an answer. But we could explore this further, like exploring the question, the query, further through some related computations. John will be going into these more than I will, but just as a quick example that I happen to like, it will say, all right, you want to integrate this. What else might you find useful about this? Maybe, for example, plotting the function x squared cosine of x, and in orange, and its integral. By clicking on related computations, it gives us all sorts of useful things that we could be doing. We're not going to look at all of them, but that's an example. We can also explore not the question, but the answer further. By clicking on the output here, we'll get some suggestions. I'm going to click on more here and click on one that I happen to like, expand, to take this algebraic statement and say, all right, yeah, fine, but I don't want those parentheses there. So let's actually multiply sine x through times x squared and times minus 2 and get it all in a more expanded out version. Or we can do what we'll be focusing especially on today and go into step-by-step solutions. If I click on, back at the beginning, click on step-by-step solution for this integral, I'm not just going to see the answer, but rather I'm going to see an explanation of steps you could take to get there. Again, people who have taken some calculus courses will recognize integration by parts, which is extremely helpful, but easy to get lost in. So this takes you through all the steps, reminds you of the rules of integration by parts, describes what all of the parts are in this particular problem, like that f is x squared and dg is cosine of x dx, and all those other nice things. In this particular problem, we had to do this more than once, that we end up with this almost done answer here, but it's got further integration needed, so does a different integral by parts with fx this time, and gets us to exactly the answer that we started out with. Excuse me. And step-by-step solutions works on more than just calculus material. Like here and by the way, it works with more than just the buttons. Before I showed how you could click on step-by-step solution and it would write out show steps and then the problem that it wanted to show the steps for. But if you know that's where you want to get, you could just write show steps and then the problem you want to do. And it'll start there. You won't have to do a second thing. Like for example, factoring this out, goes through the rules of factorization, points out that there are two numbers that multiply to -60 and add to -17, 3 and -20. So those are the things that go into, excuse me, these little parenthetical parts. It doesn't all have to be numerical either. Look at this one. X squared minus b plus a x plus b times a. X, b, and a are all undefined in this problem. But not only is the Wolfram software able to factor it, which is nice, it also can explain how it did it, or more accurately, how we as human beings could do it. It's not taking us through the algorithm necessarily that it's using to do it. The explanations are always intended for human beings, the way we actually would think about this kind of mathematics. And so it can take us through it saying, well, here we're looking for something that sums to b plus a and has, or to negative b plus a and has the product of b times a. So goes through how you would find those things and comes up with this answer. I want to point out, by the way, this isn't always going to be algebra and numbers and just that sort of explanation. Depending on the kind of problem we're looking at, there could be a mainly pictorial explanation. I happen to like this one quite a bit. Show steps limit of sine of x over x as x goes to 0, as x becomes very small and is almost 0. Now, those of you who have taken a calculus course, once again, will know that probably the more common way to do this limit would be L'Hopital's rule. Take the derivative of the numerator and denominator, both of them are 1 as x goes to 0, so the answer is 1, which is a perfectly fine explanation. But because this problem has some interesting other ways to explain it, the default explanation for the step-by-step solutions is to go for that. Here, to start us off with a section of a circle and use the unit circle definition of sine, and to show that this triangle, which draws a line instead of using the arc, is going to have height of sine x, then take all of these other shapes and come together, realizing that these various shapes are inside of each other, so they have well-defined inequalities. It's okay, by the way, if you're not following all of these explanations. We are going to, as usual, make the notebooks that we're presenting with today available after the talk is over. So this is all just to give you a general idea about how these things work. So if you want to explore them in more detail, you either could write this out yourself or you could download those notebooks at a later date. But in the meanwhile, yeah, we can use these pictorial explanations to understand that this inequality comes along, and when x is 0, cosine squared of x becomes 1. So this, whatever it is both greater than and equal to and less than and equal to 1. So it's between 1 and 1. And Squeeze theorem tells us, yeah, so it's 1, right? Definitely. So there's any number of features that could come up in a step-by-step solution in any of these other helpful things. And by the way, like I said, I have been focusing on Wolfram Alpha Notebook Edition interfaces for this just because it tends to put these things front and center. But in other Wolfram products, you can find these things as well. Like in Mathematica, for example. I'm going to give a quick little example here that I've written up already, a simple Mathematica notebook, which shows the last problem we did, show steps, limit of sine of x over x as x goes to 0, just going to hit enter there. Now you might notice it didn't actually spit out the step-by-step solution in Mathematica. That's because Mathematica is a little bit more technically minded. It assumes that you are trying to find the practical hands-on answer to these things by default. But you can expand beyond that. For example, by clicking on Show All Results, you will see the full Wolfram Alpha results of this prompt. By the way, to get a prompt like this in Mathematica, you click where there is nothing and hit the equals key. That will tell it, oh, you want natural language, and be able to do something like 45 plus 3 without using the addition symbol. It will translate your writing from English to code. And then by pressing on that orange plus sign, you can see the full Wolfram Alpha results, including step-by-step solution. And you'll also be able to see in this problem the suggestions bar. Notice that these suggestions here are not for the prompt. The suggestion bar suggestions are for the answer. So for example, if it's asking for binary form, it's talking about binary form of the number 1. That's what it's working on. So with just a little bit of investigation, you'll find these all over the place. But if you ever wanted to be looking at it in Wolfram Alpha Notebook Edition and what you have is Mathematica, just one more aside before we keep going with step by step, you can go to File, New, Wolfram Alpha Mode Notebook, and you will then see a notebook which is actually in Wolfram Alpha mode. Very handy, I think, but let's go back to our actual examples of this stuff, back in the notebook we were using before. Just a minute as I share my screen for that again. Now, I've done a few examples here from calculus, a little bit from algebra. Makes sense. That is a place a lot of people hit a wall with mathematics, where mathematics fundamentally changes. A lot of people, they're used to arithmetic, and then suddenly in comes all of these variables, and in comes these things like differentiation, and it gets very complicated compared to what it was before. A lot of people have trouble, so we build in extra help. But that doesn't mean that's the only place someone could need extra help. People could use help at all levels of mathematics, so we are doing our best to build it in at all levels. Like here we go, 4 plus 2. Of course, it'll just give you the answer by default, 6, but notice there's step-by-step explanations for that. So probably anyone who can use this program probably is able to do 4 plus 2 without step-by-step. But the step-by-step explanations can be helpful for teachers who are using this for younger students, or you could be dealing with someone who is advanced in terms of their ability to speak and communicate, but genuinely doesn't know arithmetic. Whatever your reason, we've got you covered. In these step-by-step explanations, it goes into what exactly is happening when you add 2 numbers, in this case, using the number line to go from 0 to 4 and then 2 more over to 6. And because this is something that maybe could be explained in a couple of different ways, you have in the upper right here a few options. You can use number line or math manipulatives. Oh, I glossed over, by the way, that if you ever want to just show one step at a time in these processes, thinking, I don't remember how to get started here, you can do that. Just click on show next step. It'll give you a hint as to how to proceed without actually doing it at first, quite often. But then by just continuing to click show next step or click show all steps, it will expose more and more of the explanation, starting with blocks and having you count them up. I love for myself that it understands people think about these things in different ways. And that's visible in this upper right number line versus manipulatives sort of conversation, where you can use these manipulatives for a bunch of different addition problems like 9 plus 7 going through there. But it also shows up in terms of how the default help changes for different levels of difficulty, different kinds of problems. Like, let's take 19 plus 7 here. Now, you could do manipulatives or number lines there. That could be useful. But when the program sees this, it says, oh, hang on, 2-digit numbers. This person has probably gotten to the level of addition where they're having to carry things and do math in that sort of way. So the default explanation will be in that format. Here, see, gone are the colored blocks on the number line. It takes you through the addition, carry the 1, and then giving you an answer just like that. You can work with it with manipulatives if you want, so that you can show the connection between the previous way that you were doing math and moving on like that. And at a certain point, it says to itself, okay, 29 plus 48, yeah, they're probably not doing this with little blocks that are each the size of 1 at this point. It's pretty darn confident that we're doing math in this sort of way, so the option is no longer shown there. I'm not sure if you could write that option in, but we'll just, for now, I'm just happy showing off how well this thing adapts itself to the difficulty of the problem. By the way, I don't know about you, but I like making machines make mistakes if I can help it. You know what I mean? Taking a program that's running correctly and then giving it a correct and understandable prompt and seeing if I can trick it into doing something crazy, like doing the same step 50 times when it doesn't need to, or giving an explanation that makes very little sense because the problem was worded just the right way. And I have tried to get the step-by-step solutions for arithmetic to give me that sort of craziness. I have not been successful. It's quite a bit of work in there. There was a recent question about, can you explain where Wolfram Alpha, or in this case, Wolfram Alpha Notebook Edition, excels over ChatGPT's current capability? Let me be clear about something. ChatGPT, extremely impressive program, very good. Like 4 years ago, it would have been impossible for me to imagine that there would be a program that can understand written communication as well as it does, or produce written communication that's as understandable as it is. But in terms of an advantage that this has, these explanations are reliably correct. The math in them is reliably correct. The answer is reliably correct. ChatGPT, by its nature, needs to have a general sense of what the answer is going to be, just because it learns by finding all sorts of stuff all over the internet and creating a probabilistic description of what words probably should come next. So it's going to give you something very similar to great explanations it's seen. But it's possible what it's pulling from doesn't exactly apply to what's going on here. In the step-by-step solutions you're running into here, you can count on these. You can count on these to be accurate. You can count on these to give you an explanation that is pertinent to the problem, and you can count on the answer to be correct.
And another way of sort of explaining the difference between what these different sort of AI assistant tools are built for is that ChatGPT is built to generate text. And so when you're specialized to do something like that, you are able to do that in a very impressive way. Wolfram Alpha is built to do computation, right? And computation isn't necessarily restricted just to mathematics. Actually, I have some things to show a little bit later on that get into, things that people don't necessarily realize that Wolfram Alpha has information about. But that's sort of the difference between these sort of AI tools that you can reach for. What's the thing in my tool belt that I want to be able to reach for to do a specific thing. And also another thing that we're working on showing here pretty soon is that people have done some really interesting things on, like, just people on Reddit playing around with API keys, sort of combining the capabilities of these various AI tools that are out there, right? Because, for example, there's tools that can take text and go to an image, right? Like, so, a particular model, when you're dealing with, these sort of assistant tools, is specialized to do various things, right? Mm-hmm. And so being able to know as a user, what are the things that this particular tool is specialized to be able to do, sort of helps you decide, which tool you want to reach for in any given situation.
Yep, absolutely. I mean, I think it would be safe to say that both ChatGPT and Wolfram Alpha are toolboxes. They do quite a few things, but I 100% agree with you too, John, that there are overarching goals in creating these programs, and it's worth noting which goal suits particularly well to which task. Now, up until now, I've been talking about Wolfram Alpha, and I want to be sure that we're all on the same page about what that is, because that's not the program I'm using right in front of you right now. Wolfram Alpha is a website and is a program that people use to answer questions, full of curated data, full of lots of interesting facts, interesting ways to investigate things. And all of these step-by-step solutions are coming from there. So often when you're looking for step-by-step solutions, either going to the website if you have that sort of access, or clicking full Wolfram Alpha results can be a nice way to do that. But it's worth noting that full Wolfram Alpha results is not just for step-by-step, even in this program that I'm working on now. Like, let's consider this problem. Find divisors of 135. Well, the program understands my query, translates that into code, and then the code answers the problem. I can also say to it, show steps, find divisors of 135. And here it comes. It will then do the work and explain that it did that by finding the prime factorization and then multiplying all of the various prime factors by each other to all of the powers that they could have in some combination, and getting all of those answers. Great, I like that. Probably that's going to be enough for an awful lot of people looking to solve this sort of problem, but it kind of skipped a step for me in explaining how the heck it found that prime factorization. And if you instead click on full Wolfram Alpha results, you will see that you could get a step-by-step solution for finding the divisors, but also you could get one for the prime factorization. You see, by clicking on full Wolfram Alpha results, it told us how it could go deeper into other related things that we might have wanted to know about. And in fact, that I did want to know about. I can click this to find the step-by-step solution, or, and I'll just skip over that for a second because we're going to show it in just a second. You could, now that you know that you want to find the prime factorization, you could just write that in as a prompt. Show steps, prime factorization of 135. And it'll show you the steps. Talk about that. In this particular case, it goes through steps that weren't helpful, but are very helpful as a general first step. For example, is it divisible by 2? Well, no, it's not. But yeah, that's a good first thing to check, isn't it? Because half of all numbers are. So it goes through it, checks if it's divisible by 2, last number is 5. Nope, no, it isn't. Is it divisible by 3? And the way that it checks that is not in some computer thinking way of just, well, divide by 3 and see if it is. It uses a human way of doing that, adding all of the digits together and finding out that the sum of those digits, 1, 3, and 5, is also divisible by 3. And this program knows that that means the original number is divisible by 3 too, 3 as well. So in this step-by-step solution, it can give you useful ways to do this and similar problems. Heck, I was going through an example of this, show steps prime factorization of 34,254. I picked this number just by plugging in 4 random digits, 3, 4, 2, 5, and then I added one at the end that would make it divisible by 3 because I know that sum of digits sort of technique. But then having done that, just started to look through here, and I ran into this. Show that this factor is divisible by 11. The alternating sum of digits of 1903, 1 minus 9 plus 0 minus 3, is negative 11, which is divisible by 11. That means that the original number was 2. I never learned that. I've studied math for years. I studied the teaching of math for years. I never learned that. This thing taught me something useful in the presentation that I'm giving today. Like, I just love that. I love that this thing can give useful hints across the board for the sort of way that you can solve these sorts of problems. I want to be clear, though, I'm a big fan of the advanced stuff. I know I've been lingering on some of the arithmetic-heavy sort of applications of this, but I love the advanced stuff too. Here's an example. Prove by induction that the sum of the numbers 1 to n is n times n plus 1 divided by 2 for n greater than 0. Now, that's a familiar equation to anyone who's studied some number theory, maybe some discrete mathematics. But you'll notice when I put this in here, it did not prompt me that it could give me step-by-step solutions. It can, but it doesn't always do that when that's an option. But you could just click on full Wolfram alpha results, and having clicked on it, run it and see that there are step-by-step solutions available. But also, since I happen to know they were available, you could just write that in the first place. Knowing that's what you're after, you could write in step-by-step, prove by induction that this is true. By the way, induction is something that is a formal method of proof. Probably a lot of you know this, but that tries to prove things through kind of a domino effect by setting it up to show that if this is true for some situations, then it will also be true for other situations, and then proving it for one particular case and letting that prove all the cases after it. Beautiful technique. But if you're not familiar with it, that's okay. You can look over this great explanation later, but we're going to be going over it a little too fast for someone who's never seen it before. But for someone who has, you can see that it goes through the steps of mathematical induction very nicely. Talks about base cases that you need for induction, talk about the excuse me, the inductive assumption, just going through all the steps necessary, making it clear what you're doing at every point, keeping an eye on the end result that you need to get, just a solid induction proof. And by the way, this isn't just available for 1 or 2 examples. I threw in creating this presentation, full disclosure, I just Googled nice induction examples, not looking on Wolfram Alpha, looking in general, just to see what I could find. And I found that somebody said, prove 2 to the n is greater than n for n larger than 0. By the way, this inherently assumes we're just talking about integers, whole numbers. Excuse me. That's something that may seem pretty darn obviously true, to most of the people watching this, and it is, but I found that obvious things are often the hardest things to prove if you have to prove them rigorously. So I just liked that even that problem, which I hadn't seen before, I hadn't seen as a common induction problem, is one that's available to explain and solve through step-by-step solutions. And it also, like that sign limit, gave a little visual to help show what's going on, or at least be just that tad bit more convincing. I love all of these mathematical examples, but it's not just for math. John is going to be talking about some other great areas that these functions and functionalities can be used. So John, I'm going to turn it over to you now. And
awesome. Yeah, so a couple things in the chat. One is that we should have a link to, if you're curious about, are there APIs for Wolfram Alpha? The answer is yes. There are a lot of documentation, and there's several different types of APIs specialized for sort of different use cases. As I briefly mentioned before, we're looking at putting together a short video sort of explaining, where do I get my API key and all those sort of questions that someone might have if you are not familiar with doing that process and are sort of curious how you can sort of build your own sort of interesting applications and things that, again, there are more and more really awesome tools that are out there that people can use that draw on like all kinds of sophisticated computation in order to be able to produce useful results to people. And so one way of sort of accessing these things are through APIs that you can use to sort of call these things and you put the results together. So as I said, we'll be doing a short video that just sort of focuses on that topic here before too long. But if you want a sneak preview of some of the things we're going to talk about there, feel free to browse through some of the documentation for Wolfram Alpha API keys as well. Also, we had another awesome question in the chat, which was, what are some applications of step-by-step to classroom setting? So I'm very glad you asked, because this is a topic that I think is really important and is also really important to help speak to your students about. So one thing that we want to do whenever we're sort of working with students is we want to help them develop metacognitive skills. Metacognitive skills are really important. And for those of you who have studied the nuts and bolts of education, you'll know what that means. But metacognition, basically in a nutshell, just means thinking about thinking, right? So it's one thing to think about a problem, but it helps us build understanding and build higher order skills if we also think about the thought process that leads us to be able to solve certain sorts of problems. So there's a lot of really interesting literature on this, and there's a long history that I want to briefly get into before getting back into the nuts and bolts examples here. So one thing we want to keep in mind are, so what are educators actually trying to teach students? So if you're a teacher looking for advice, or if you're a student who happens to be watching, one thing that often gets left out of the teaching process is the step-by-step for teaching, right? I mean, it's happening implicitly on the side of the educator and on the people who are designing curricula and all the tools that go around it. But students often, just because there's a lack of time in many settings to go into these details, students sometimes are wondering, why are things being taught in various ways? And sometimes the answer is just, oh, well, it's been done that way for a long time. But hopefully, and in this case, there are sort of reasons why things are set up in different ways. So what are educators actually trying to teach students? So as you should also definitely, if you haven't already, check out our interview that we had during the last Outreach live stream with Colin Chapman, who had some really, really fascinating things to say about engaging with students sort of at a level that many classrooms don't start at for various reasons. And so when you're teaching, you want to always think about the sort of metacognitive ladder of skills that you're trying to help students be able to engage with. And metacognition, like many things, is sort of a developmental process where, just like abstraction is something that very young kids struggle with, metacognition and related skills and Also, another one worth mentioning is executive function, right? So there's a cluster of skills that sometimes go by the name executive function. All these things are developed in students along these developmental pathways that are sort of unique to every student. And so when you're thinking about, okay, what are we trying to do? We want to help students frame their own questions in these clear, actionable ways. And if students are able to frame their own questions in these ways and then act on that, then that will help them reach their goals, no matter what their goals are once they leave the education system and are sort of out doing the things in the world that matter to them, right? So as part of framing your own questions in a clear, actionable way, it's also important to have the skill of coming up with a plan of attack to answer particular questions.
Yep.
And then based off of this sort of what's my plan of attack to answer a particular question, we want automaticity, which basically just means that you've practiced something to the point that you no longer have to be concerned with the details. It's just sort of an automatic part of a larger process. You want automaticity with basic algorithmic knowledge, right? And so we want to be able to facilitate students working at the top of this metacognitive ladder. And this has a lot of benefits for building student engagement and getting buy-in to their whole educational process. But it's also true that these higher order skills are informed by your familiarity with the sort of skills that are further down that metacognitive ladder. And so what do we do about this, right? This is sort of one of the driving questions of a lot of sort of modern education theory is how does one help students develop these metacognitive skills and these higher order thinking habits like critical thinking, given that the more algorithmic sort of rudiments also affect your ability to articulate things in these ways. So let's briefly just get into, I want to show off a couple of Wolfram language functions that are very handy. So Wikipedia data and word cloud are awesome functions to play around with, especially if you're an educator. So in a nutshell, constructivism is a theory that has to do with how people learn. And the central sort of claim of constructivism is that it's not really possible to just transmit knowledge around, right? Knowledge doesn't work the same way that you would, hook up a Ethernet cable from, one person's ear to another person's ear and just transmit knowledge from one to the other like you could with the computer.
As objectively cool as that would be.
Right, yeah. The sort of central claim of constructivism is that instead of that, people build up their sort of own internal model of what's going on based off of two things, based off of their prior experiences and knowledge and based off of whatever new stimuli are coming to them. And so a fun thing you can do with any given piece of text is make word clouds. So we can sort of see that what is constructivism about? It's about learning. You'll notice that the words related to students are larger here because they have a higher frequency. This is how we make this word cloud in this example, have a higher frequency than things like, the facilitator, instructor, or teacher, right? So one thing that frequently goes hand in hand with sort of a constructivist philosophy is student-centered learning. And so another really important branch of constructivism that I want to talk about is social constructivism. And so, people sometimes think of, oh, Wolfram Alpha, that's good for doing math, but there's other cool stuff in there as well. So you can ask for an image of, various people. So for example, Lev Vygotsky is a very influential figure in the history of, educational theory. And Vygotsky's students took many of the original writings of Vygotsky and developed them much further. If you go and you look for the full results for various people, you'll see that Lev Vygotsky himself only lived to the age of 37. And so then some of the writings were turned into other more developed theories by some of Vygotsky's students. And so sometimes it's an interesting exercise to try to figure out, did Vygotsky say it or did Vygotsky's students say it, right? But anyway, one of the important things that, and also another fun thing you can get are sort of Wikipedia page hits history. You can see actually that with a lot of people and topics, they follow sort of a yearly cyclical pattern. Whenever you see this, I have no idea if it's true, but I'm going to assert that these sort of cyclical patterns often fit with curricula. And that when there's a figure or topic that people read a lot about during certain times of year, you'll sort of see these yearly things. But
like the dips are in summer or in January or something like that.
I'm going to make that wild assertion without proving it in this example, just because I only noticed this a moment ago. But it's sort of amusing, and I would bet that if you look into that, you can pick out exactly what months these things are happening. And I would also bet that this goes along with the school year. But anyway, so. what does constructivism have to do with showing steps and all this sort of stuff? So social constructivism is a viewpoint on educational theory, which basically says that students, no matter what you try to do, students are going to wind up building these internal models of how stuff works based on their interactions with you and with others and with sort of artifacts out there in the world that they interact with. So you might say that any piece of writing is sort of an artifact that someone was trying to convey ideas through. And then this is sort of one channel that people are going to construct their own internal models of how stuff works. So if we look at, how are we going to engage students? Because we do sometimes want to touch on sort of very basic algorithmic knowledge, because if you're working in a laboratory, you have to know, how am I going to, for example, prepare a particular solution with a particular molarity, right? So if I want to make a saltwater solution with a particular molarity and I want a certain volume of it, this is sort of a basic algorithmic knowledge problem. But do I want to lead with that when I'm trying to, get student buy-in and engage their higher order thinking skills of framing their own questions? It's maybe not the thing to lead with, right? Like in my introductory lessons, what I'm going to do is I'm instead going to want to, have something which the students find exciting and engage their curiosity and or have to do with problems that matter to them, which is in most cases probably not going to start with the algorithmic knowledge, right? It's going to start with some applied problem that they're curious about. And so what you can do is you can use these programmatically generated explanations in order to show, yes, okay, this is an algorithmic thing. You can even take a look at, how do I do this? And I can model, how am I going to eventually think about this algorithmically? Well, at first, just saying, all right, I want to make the solution so that I can go do the rest of my laboratory. And then we can return to these sorts of things. Now, another really important thing to emphasize, if I click this show next step, so you notice there's two buttons here. There's show all steps and show next step. The show all steps is for convenience so that you can see all of them at the same time. But again, we want to help our students build their metacognitive abilities. So that's not something that you just sort of know how to do if you haven't seen and had this process modeled for you. And your students are not going to have seen or had this process explicitly modeled in a lot of cases. So what you can do is you can say to students, okay, well, there's two things we can do here. We can either show all the steps, or what happens if I click this one, I get an idea of a plan. Before I start going through the rest of the steps, this is again engaging that higher order thinking of, before I start going into the individual steps, I need to get my overview of what am I trying to accomplish here when I'm solving this problem, right? And that sort of first step, after you've clearly stated the problem, then, okay, now I need a plan to attack this problem. And then I start getting into the more sort of algorithmic skills that, we spend a lot of time in some cases teaching, but those algorithmic skills are not really the ones that we're aiming for at the top of that metacognitive ladder, right? We really want students to be able to frame their own questions, draw on their own curiosity, solve problems that matter to them. And these other things are part of being able to answer those questions, right? But it's not necessarily what you want to lead with when you're building that initial engagement in a lot of times. And so that's a really important point to emphasize. Okay, so then another thing that you can do is you can sort of craft classroom experiences so that they are built around, oops, excuse me, wrong button. You can craft classroom experiences so that they aim toward particular learning goals. And so in this case, we have a set of classroom data. So this classroom data is coming from, you hand your students a kit where they say, all right, I'm going to build a little model catapult, and then we're going to take data and we're going to use this data, we're going to analyze it, and we're going to figure out, how do these things work? How accurate are they? How can we understand their sort of bounds on their accuracy from this mechanical thing? And then, that can lead into the rest of the sort of skills that you're hoping to cover, right? Because if you start off saying, okay, today we're going to learn about standard deviation and mean and these sorts of things, okay, you'll get some buy-in from students, perhaps, if they already have that contextualized as part of their own skill set that they want to develop. But you'll reach many more students if first you say something like, okay, here's a catapult set. let's see who can have the most accurate results after we test these and see how they kind of behave. If you frame it that way, by sort of cleverly incorporating some applied aspect to what you're doing, this does a couple of things for you. So one is it allows students to sort of draw more on those higher order problem solving skills and then motivate the algorithmic knowledge. But it also sort of really makes it so if this is your data set, so this is a bunch of numbers. So let's say that these result from aiming your model catapult, and this is where everyone's, so you pool all the results that everyone had from the class perhaps, or maybe you just do 100 trials with one model, who knows, various ways of doing it. Depending on your class size and time that you have for a lesson like this, you might do different amounts. But you can already see, if you're interested in talking about sort of standard deviations and means for this data set of 100 things, suddenly this is not in the scope of something that you would want to solve by hand anymore, right? So,
John, quick question. The X and Y axes on here, what do they represent?
So in this case, when I did this with students, this was just measuring, distance one way and distance the other way away from where you were aiming for.
This is a spatial thing. Cool.
Yeah. So this is just space in one direction and space in another direction. Good question though, because you always have to wonder about that when you're talking about a physics thing. But yes. So another thing that you can do actually is, if you want to let me initialize this and do this. So let's say that we want to add those labels to something like this. So after you've got that, one thing that you can do is you can use the suggestions bar. Let's say I forgot my labels. I can just add that, and I can have my x-axis be so distance in meters. Let's say we'll make this distance in meters, let's say, and then we'll go ahead and hit done there. And so then we will wind up getting whatever we've put in here as part of our plot, right? So that was done again through, I've got something, I want to modify it. If I use these suggestions bar down here, this is a quick way of adding things. And then again, as with most things in Wolfram Alpha Notebook Edition, if you're wanting to also have as an additional learning goal, how would I do this kind of stuff in Wolfram language? There's options for labeling axes, and there's options for if I want to set the plot label. So, let's say that I want my plot label to be, let's not get too creative here. Let's just say my plot. So if I want to just add something in like that and then run this, now I've got my plot label there. And so, being able to quickly change these sorts of things and kind of get the gist of how they work so that you can go in and make changes is one feature that I really like about this. So, so after you've got, your data, so you've taken your students and you've set them down with their models, and they've, built them and they've tested them and they've got some data, you can get them excited to sort of learn advanced concepts. So this is plotting the same data set. Notice that the axis scaling is a little bit different with these, so that's why it looks a little bit different, but this is the same data set. And there's these various functions that you can use and different methods that you can use. So this is a method that sort of doesn't make assumptions about the normality in the data, to the extent that if you just say, well, here's a multi-normal distribution. So in other words, a normal distribution in one way and a normal distribution in the other way. And then I want to fit to that. This is a question when you're modeling things. Do you want to say, all right, I'm going to remain a little bit more agnostic about the underlying model and then just, let it rip? Or am I going to say, no, for whatever theoretical reason, I think there's a particular model I want to fit and go in that? So again, by sort of getting students excited about the things they're building toward, that sort of motivates the examples where now, after we've sort of seen some of these things, I'll come back to this plot in a minute, but after we've seen some of these things where, okay, I want to know what's the mean and the standard deviation, instead of, having it all one way or all the other way, where, so, I wouldn't want to calculate this by hand. I wouldn't want to take, 100 sets of XY coordinates and figure out their mean, and 100 sets of XY coordinates to figure out their standard deviation by hand. That wouldn't be fun for the students or anyone, right? So instead, what we can do is we can use computers to help with the things that computers are really good for, like handling all this. But we can also sort of work with some other examples just to build intuition with our students about what's the computer doing roughly, so that I kind of trust the results and understand what the results can be used for in these situations. So before getting into detail about that, I also want to remind people that there's some interesting blog posts that have been done recently. So there was one about computational foundations for the second law of thermodynamics. So this is another example where you can sort of, say thermodynamics to your students, and that sounds very exciting and something that's very far off in terms of their course of study, unless you're already a student who's getting into these things. But the same concepts that apply in thermodynamics. So for example, there's this very important concept called coarse graining, where you take some data and then instead of keeping track, like is shown in this version of the plot of where each little data point landed, what you can do is I can draw bigger boxes around each thing. And now in this plot, I'm color coding. So there were more that landed in this red box than there were that landed in this purple box. And the green is somewhere in the middle. And you can see just with your catapult data, right, that just came from playing with toy catapults and seeing where they land, you can get into these other concepts like coarse graining. And so if I continue to adjust the box size, right, so here you'll notice that the axes are not changing in the distance that they're measuring. All we're doing here is instead of counting each little thing as one hit, we're drawing some grid lines on here. And we're saying, okay, if there's two things in the grid lines, make them a different color than if there's only one thing. And if there was nothing there, leave it without a color. And so I can adjust this coarse graining to see how what looks like just a bunch of scattered data might have some structure to it in this other scheme of coarse graining. And if you want to know a little bit more about what that has to do with various concepts in physics, you can check out some of these blog posts that were put out recently. So that's not quite exactly show steps, but just wanted to remind people that's a thing out there that is kind of cool and you can check it out. Okay, so back to what are the classroom examples of showing steps? Let me also take a quick look at chat and see. So yeah, it looks like that there were people who were helped understand solutions when learning. Yes, so let's get into that a little bit. So instead of only having, either calculator or do it by hand, what we can do is we can find nice teaching examples where it kind of makes sense to do something by hand just to see how it works. So if I want to calculate the mean of a couple of numbers, now I've framed why this is an important thing to sort of have an idea of how it works, right? Because if I just start off by saying, okay, I want to calculate the mean of a couple of numbers, you're really inviting that question from students of, well, why would I want to do that? Whereas if instead we start off with some applied thing, we can sort of end run that question in the first place. And now, oh, I want to know how to calculate the mean of some numbers because that's going to help me have a more accurate catapult model in this example, right? And so if I go to show steps, again, help your students build metacognition, right? So look what happens if I don't click show all steps first, if I just click show next step. We get a hint, state the definition of mean. So now your student can actively think about this, right? You can use this as a learning tool to say, okay, wait, what was the definition of mean? Do I know what that definition is? If I don't, then I put a little mental note that, okay, I need to actually memorize that at some point to know what the definition of mean is.
Of course, you could also use this notebook to look it up.
You can. And so if I keep looking, I get more details filled in as I go. So the mean of a list of numbers is given by the sum of the elements over the number of elements. Okay, so nice natural language explanation. And if I keep going, I want to, okay, what's the sum of the elements going to be? So in this case, with these three elements, the sum is that. And how many elements are there? So there's going to be, that many, and I can continue going and I can evaluate the sums and things like this. And so we can, instead of jumping to the end, we can have the student at each stage query themselves, right? Building that skill of knowing what it is that they already know and what it is that they're not sure about yet. And we can lean into that so that they're able to have a better sense of where the boundaries of their knowledge are so that they can more effectively study, right? So we can use tools like this as a metacognitive helper. Another thing that we can do is if there's a term like standard deviation. So this means different things in different contexts, right? Am I talking about the sample standard deviation or am I talking about the population standard deviation?
Very important question.
Yeah, and so clarifying assumptions is another important metacognitive skill. And so by getting prompted whenever you type something in, oh, did you mean this? Or are you assuming this meaning or that meaning? That's another way of having an internal check of, oh, wait, did I mean that one or did I mean the other one? And so as a really good example here, so if I want to show steps for the standard deviation, this one, even though, yes, okay, I really want to emphasize that you can go through one at a time because that's a good metacognitive aid. If I just want to skip somewhere because I've already done that exercise and now there's a detail that I want to see. Oh, right, okay, so the sample variance is defined this way. And then I might have further questions about, what is the mean and those sorts of things, but we'll assume that we've got to that point. So again, by using these sort of explanations, you can identify other things that you might want to review. You can get definitions. You can also get that metacognitive aid of being able to decide when do I want to look further versus when, no, I'm confident I got it and I'll just check at the end, right? So let's go back to the population standard deviation then. So we can also use this as a way to compare various explanations. So I've reproduced here the population standard deviation, and we see that it's a different number. The students will rightly wonder, well, why? That must be defined in some different way. And so if we go to the point where we define this, okay, so in this case, the difference between the population variance and the mean variance is a difference in the denominator. And again, as the instructor, you can sort of help frame the learning goals. Do you want to get in the whole topic of degrees of freedom when you're doing measurements and how, if you've already got a known mean, then that reduces the number of degrees of freedom in the actual data that you have? Well, okay, that's a complicated thing for, some context, but for other contexts, that's exactly what you want to get into. And so again, you can use tools like this in order to sort of help students get a sense for contexts that it might be a little bit beyond what they're currently interfacing with. And they can sort of help explore that a little bit. But as the instructor, you can frame what should the students be directing their attention towards so that they can, get the most out of the experience. And that's one place where it's really nice to have a human in the loop whenever you're dealing with any computer tool. Okay, so that's the explanation for that one. So another thing that you can let students do. So again, we want to get back to this idea of students build knowledge based off of their experiences. So by looking through some related computations. So let's say a student is looking around here and pulls up kurtosis. What in the world is this? Well, apparently it's, this number off of this set, but now I'm curious, what does that mean? So I can ask for the definition of kurtosis. And so I can say, well, okay, this is something to do with distributions. And if you're a student, you may or may not sort of know what that means yet. If you are ready for that definition, okay, great. That reminds you what the definition is. If you're not ready, you just get the sense of exploring, there's this bigger world out there that I can continue to learn more about. And part of the role of the instructor is to help guide, oh, you've stumbled across these things. You'll use this in, this other class that might not be the one that you stumbled across it in, but isn't it cool that it's out there, right? So
now we have just been going on for an hour, which is the amount of time that we were planning on going in a minimum, but there are a few more things we wanted to talk about, and there are a few more audience comments we want to get to. So if you have time to bear with us, feel free to stay tuned. We are going to keep going for a little bit.
So let's see. Also, if you have any examples that you'd like to share of ways that you've used really any tool, but especially Wolfram Alpha for helping you learn in particular classes or particular contexts, I'm sure other people that teach and take those classes would love to know them. So feel free to share. So the other thing that we want to do is scaffold for symbolic thinking, right? So just like metacognition, just like various executive functions, like being able to have a little bit more intentional control about where you're directing that spotlight that is your attention. Abstraction is another skill that we're aiming to help students develop, right? And so for students at a particular level of prior knowledge, it might make a huge amount of sense to keep the level of abstraction only relevant to introducing the concept of a single variable, right? This is traditionally done where, okay, I've got the concept of numbers down. I kind of understand that I can form numbers into equations. Now I want to introduce single variables and, get into that. So depending on your level of prior knowledge, that might be the eminently sensible thing to do. Now, you can, in this example here, really want to, again, emphasize that point. You want to give your students direct instruction about the best way to use an explanation, right? So what is the best way to use an explanation? Well, one way to use it is to just read it. But the best way to use an explanation is to go through it a piece at a time, seeing if you can anticipate what it's going to say, right? So if a student wants to solve this and says, oh, I do not feel confident in my ability to do this, what's a way I could do it? You can, again, and another trick for teaching is repetition is definitely a good thing, right? So this is why I'm mentioning this multiple times in a row, is that anytime that you want your students to be able to get the most out of an explanation, having them sort of anticipate what comes next before checking, does what they anticipated match with reality? That's a really good way to sort of critically think and build memory and build experiences that then can be turned into their own internal model of how stuff's working. So the hint here, if I just click one, is I want to isolate terms with X on the left-hand side. Now that reminder, again, one of the whole points of constructivism is that the critical thing is, what is your student's level of prior knowledge that they're bringing? Depending on the experiences they've had, that one hint might well be enough for them to go ahead and do the rest of the thing. And they have the freedom to ask for that hint and decide, what is my level of confidence with this? Did I not need any hint and I can just, do it? Do I need to sort of use this as a way of clarifying what my study needs are if I'm wanting to understand these algorithms, but am not sure where I'm tripping up? You can compare where is your process tripping up compared to what's the explanation saying, and that's a way of doing it. And so then I get a concrete example. Let's say that the hint was not enough for this particular student. The student wants to know, okay, concretely, what does it mean to isolate X? Well, in this example, we go through the arithmetic and we wind up reaching a place where we get here. And then the student might say, oh, I remember how to do this one. This one's easy for me now. It's going to depend on every different student is going to have a different response to reaching a point like this. So determining when a student is ready to start building abstraction into a higher order thinking toolkit is really a lot of skill and art on the part of the instructor, right? This is where having a human in the loop can be really important, because for many students, it might really make sense to view this as a totally different problem. Let me show all the steps and then collapse them again. So I can scroll back up and sort of show where this came from. So for many students, it might make an immense amount of sense to view solving this problem as a genuinely different problem than this. Now, that depends on what's their level of prior knowledge, where are they developmentally, are they ready to start abstracting some of this? Because when you're able to take a bunch of problems that might have seemed like separate problems and realize, wait, these are actually the same problem, just with some little details different. That's a really powerful thing, and kind of what we're aiming for basically anywhere you look in the curriculum, right? The goal is to have a familiarity with the algorithmic knowledge, but the reason that you ever want familiarity with algorithmic knowledge is so that you can engage your higher order thinking skills. So depending on where you're at, you can generate show steps for any of these particular examples of something that could be abstracted into a more abstract is the right word, problem. However, for some students, they might be ready to go ahead and take that step and abstract away, right? Say, oh, wait, it actually kind of didn't matter what the numbers were. I'm doing the same sorts of things in all of these examples. So I can see steps and I can see what this looks when now I have a goal, which is to solve a linear equation, but I'm kind of getting away from that idea of like a particular number being the important part. I'm abstracting away the details of the arithmetic and thinking more about like, okay, algebraically what's going on.
It's similar to the factoring example we saw earlier.
Indeed, indeed. So what you can do is you can have your students compare various explanations like these, right? So if your student is sort of, and this is a term that comes from constructivist theory in what's called the zone of proximal development, right? So this is something that means the range of skills that your student hasn't quite yet mastered, but is really kind of ready to start mastering and where it's good to challenge them. So let's say that you have a student who is ready to start abstracting away from particular examples of equations like this, and you're ready to really go for that level of abstraction. You can have them compare these different explanations, and seeing the explanations next to each other can help them understand, oh, it is the same thing that I'm doing in what I used to think of as different problems. This is all really the same problem I'm solving. So another activity that I'll suggest that sort of touches on the social dimension of learning. So a really cool trick that you can use to get people to think about their own thinking is ask them to think about someone else's thinking, and implicitly they'll think about their own thinking at the same time. So Noah was already showing that arithmetic has some really great show steps. So you'll notice here that for this particular example, there's long subtraction that, if we get down into the details, gets into the concept of borrowing. I can also use...
I have to laugh at this example because although a perfectly good example of borrowing, it's one of the least useful ones. We took 13 minus 7, borrowed a 1 to make 13 minus 7. It's one of those situations where the algorithm is correct and handy, but also it's understandable why someone would want to switch off it to a different option, like John's doing now.
Yeah, so like, for example, this is not typically what you would use explaining, how you would do this problem, even though it does work. It's an explanation, but a more common one that you might see is to use the number line, right? So if I show steps using a number line for a problem like this, I get this concept of, numbers and addition involving what we might think of in later contexts as, adding vectors and things like this to add up to traveling different distances and things like this. But you don't have to call them vectors. You don't have to, get into the fancy terminology. Your very young students will still be familiar with the concept that if I go 13 steps backward and then 7 steps forward, that's the same as some number of steps backward, and I just have to figure out how many that is, right? And so you can have these different explanations for the same sort of problem. So then the activity that you can do with your students is you can ask them to analyze each of these explanations. So there's the borrowing algorithm, the geometric intuition with the number line, and then also this other one that's just called just simplify it, right? So this just simplify it is also a perfectly valid explanation. So what you want to ask them then is, what prior knowledge does each of these explanations require in order to make sense? So for example, this just simplify it one, well, that makes sense if you know that the arithmetic works a certain way, right? Like if this problem comes up in the context of like an advanced algebra class or something, and you're looking how to simplify a coefficient, that might not be the most natural example, but just simplify it is a good explanation for some students in some contexts, right? But it's not a good explanation for all students in all contexts. And so what you want to ask your students is, given these different explanations, what are all of them assuming? What's there before you ever get to step 1 that you need to know in order for this to make sense? And then you can ask your students, what classroom activities from your own past does each of these explanations remind you of? And they're going to have a list of things that they remember doing, right? And this is engaging their prior experience to help them build their internal model of how something works. And then this is what I think is the key to an activity like this, is then you say, okay, imagine that you were teaching someone else how to do this. So in what grade levels do you think it makes the most sense to give each of these explanations? And then what they're going to do is they're going to connect their past experiences where they remember hearing some of these explanations, but they might not have seen all of them, because again, the key is that they're all coming with different prior experiences that's going to really affect the way that they are able to not analyze, the way they're able to synthesize new knowledge, right? And so by helping everyone discuss these past experiences, you're allowing this class to pool their past experiences in this social interaction, so that then they're able to draw on other experiences that now they're only hearing about that some other student might have had, but they're able to now have a richer set of experiences to draw on. The other trick that, as a teacher, this is really handy to listen to this part where you ask, what classroom activities from your own past do these explanations remind you of? You will never be surprised if you, or I should say, it never fails to surprise if you ask students to talk about some, set of learning activities that you might have assumed were pretty common because they were pretty common among your own education. A student that had a different set of schools that they went to might have a totally different way that they were introduced to a topic. And so you never want to assume that, even if there's a very standard way of teaching something, a particular student might have literally never seen it before. And so activities like this can help you get to the bottom of that as an instructor and understand, oh, the fact that you're not confident in this algorithm might have to do with the fact that this really common activity that a lot of students had is not one that you've done. Well, I guess we can just, engage with that activity, and that might be what we need in order for this algorithm to suddenly make sense. So really, last point I want to make here, before we get into like a sort of larger philosophical discussion, is that any activity, including this one, and I should say another thing that you can ask them to do first, ask them to come up with a fourth, method of explaining that isn't reflected in any of these three, right? And so one common one that you might have seen before with manipulatives of different colors that can combine in order to cancel. But other students might come up with analogies that involve money or purchasing ingredients for cooking or all sorts of things, right? This is helping engage their creativity in order for them to make their internal models that they're building more easily able to interface with tasks that they're going to do, because when they're able to explain their internal model, they're having to clarify it for themselves rather than have it be implicit as part of their thought process. So any activity, including this one, requires buy-in from students. Otherwise, they might just not do the task. So framing tasks in terms of your students' own sense of skill development by reminding them about metacognition, reminding them about this sort of hierarchy of metacognitive skills that go from, again, I'll just show briefly back up at the top, automaticity with basic algorithmic knowledge can be handy in various contexts. But what is usually more immediately important to people is to be able to frame their own questions in a clear way. And in between those two is coming up with a way to solve particular problems that connect these sort of big questions with the nitty-gritty details of what you're familiar with. And so in order to have that buy-in from students for activities, it's really important to always remind them how is any particular thing that they're doing connected with this sort of most creative, most immediately engaging, and oftentimes very applied sort of question and thinking that students are just naturally going to be drawn to. So that's some ways that we can use things like this in terms of classroom practice. Now let's check out in the chat.
Yeah, there were some interesting things there. One that got my attention was a question, is there some form of ChatGPT-like thing and AI and natural language processing going on the back end to translate in Wolfram Alpha Notebook Edition from English description of what you're doing to code? And the answer is yes, we are using Wolfram Alpha to do that, which uses natural language processing. Now, how exactly does Wolfram Alpha translate from English into code? To quote Tevye, I'll tell you, I don't know. John, do you happen to?
Well, so some details of this are probably not ones to share live, but
right. There's some proprietary stuff.
Yeah, I will share an example. So these images. So speaking to the larger question of, are there machine learning techniques that happen, behind the scenes for various things? The short answer to that question is that yes, there are machine learning techniques that go on behind the scenes for various things. And so the difference basically between these two methods gets to that question. So this particular method that generates this sense of what the distribution of this data is, this is a method which I think it would be fair to call a little bit more machine learning oriented. And in fact, in many Wolfram language functions, there's an option called method. And if you set the method to different things, it will employ different particular techniques that are available. So one thing that there's a function called learn distribution that you can just apply to data, for example. So this data, if I apply learn distribution to this, there's various things that will happen that will say, okay, what would be a good method to use for this data? But you're also not, whenever there's a choice of method, you're not constrained by the one that automatic settings will point you toward.
Yeah.
You always have that ability to sort of go in and change, okay, I actually, for various reasons that are unique to the problem I'm solving and to my own sort of theoretical model of what I want to accomplish, I pick this method as opposed to that method. And so the short answer is that, machine learning is something that can be used as part of Wolfram language. And there are various functions, for example, learn distribution. There's in fact a whole core area page. If you go and maybe I can link in chat in a little bit. There's a core area page that has then links to other individual guides about various topics in machine learning. And so you can sort of see how are things like that presented in Wolfram language. And also there's a whole other blog post. So I linked this blog post about thermodynamics in the notebook. If you haven't already checked out, there's a blog post about how does ChatGPT do its thing?
Yes.
It's a very, very cool blog post that has some nice visualizations of what does it mean to train a function? What does it mean, what does it mean to have a neural net trained to replicate a function? What is a generative transformer that can create text, right? A generative pre-trained transformer in the case of GPT, right? What do these sorts of things mean? So check out that other blog post that we can put up on the screen here in just a second, and also probably have in the chat before too long.
I will say that regardless of the exact mechanics of how natural language is transformed into code in this, I do not believe that it's done by just having a list of prompts and then the corresponding code that it turns into, because the translation mechanism we're dealing with here is extremely flexible. It can turn lots of different equivalent phrases into the same command. You can see some good examples of that in one of the first live streams this particular academic outreach group did, Wolfram Alpha Notebook Edition, Introduction for Wolfram Users. There's some good examples of that sort of thing in there.
And notice here in this one, so we had some data, and I just said plot, and then out of that we get what would be called in Wolfram language a list plot. Now I could just ask for a list plot in natural language, but if I'm using natural language, I might not know the difference or when I would want various plots. And so there's things that happen that sort of try to figure out, okay, instead of what you said in natural language, what might you have meant in Wolfram language? And so that we can do an output which makes the most sense based off of the data that we have here. Yeah.
There was also a question, a darn good question. Wolfram Alpha can solve math problems. Can it also generate new ones, like for the purpose of practice? And the answer is absolutely it can. We don't have prepared material planned for that today, but that would definitely be something good to go into another day in detail. John, I see you typing. Are you wanting to throw up a quick example of this?
So there's a great place that you can go here.
It's worth noting that the feature we're about to show you is one that's in Wolfram Alpha, the website, but so far is not in Wolfram Alpha, the Notebook Edition or Mathematica. Everything else we've been talking about today is available across many different versions of our technology. But this one you're going to find specifically online.
And a really nice thing about the problem generator is that, actually, let me sign out here just to. So also, again, there'll be something that we'll get into related to APIs and stuff like that in a shorter video. But if you are signed in to a Wolfram Alpha account, you can go and check out APIs and stuff like that by going up here. But let me sign out real quick just to show that you can still access this even if you're not signed in. Okay, so I'm not signed into anything here. This is just, and you can see my screen here with Wolfram Alpha. Yeah. So, the Wolfram problem generator, if I go to, let's say that I want to have my student practice arithmetic. And the other thing worth showing here is that instead of browsing by concept area, I really like thinking about these things by concept area. I was, fortunate enough to not have to worry too closely about, what did I think was important to teach? How is that aligned to standards? In the most cases, it would be anyway, but sometimes it's a question like, okay, here's this really cool thing I want to teach or use. Is it aligned to a standard? Well, if you're looking at the Common Core standards, these are sort of nicely organized if we have a, let's go to a totally random one. I don't know. I guess fractions. Fractions is one that's nice. So, and then let's say that I want to do some simplification of fractions. So again, this is, I'm not signed in. This is just the website Wolfram Alpha. Go to wolframalpha.com/problem generator. You can also Google it and it should come up. And so then I get, this. So let me get this one. And got this one. And so then I get another one. Let me just say that this is 6. I know it isn't, but let's see what happens. Oh, that's not correct. But I get this nice hint that says I want to reduce this to lowest terms. Start by finding the greatest common denominator or greatest common divisor between these two numbers, and I can sort of go from there in order to figure out, okay, what's this going to be? So yeah, the problem generator is a feature that you can go and look here, and you don't need to be signed in to use it. It's just a thing that's out there.
Love that. Thanks, John.
Yeah. How much can the, so there's a couple different types of APIs depending on what you want to do. And
again, we're going to go into APIs specifically at some point.
Yeah, so this is not the main topic of today, but since we've got questions on it, we can go ahead and share. So if you go to—
The question was, for those of you who are on the other format or watching this afterwards, how much can the website do that the API cannot do yet?
So this simple API is one that just generates you a image of whatever the query that you want it is. Let's see, do I have an example on the page? Yeah. So what I did here, just to back up for a moment for anyone who is not familiar with this being a thing that you can do. So there's these various pre-built APIs that you can go and take a look at. So you see that there are quite a few, right? So there's a simple API that does the simplest possible thing. It just generates this image that doesn't have any fanciness to it. It's no longer interactive because it's just an image, but it shows what do you get when you ask Wolfram Alpha a particular question, right? So this is the simplest possible thing. So that is the simple API and is documented, as you might expect, under the simple API reference. If you go and you look at, so this is the site products.wolframalpha.api. It has information about how you can get started, what the standard pricing for APIs are, and then let's say that you want to do something that is a bit unique. So, if you have something that you're curious about that doesn't seem like it's quite totally covered by the documentation that's out there, you can always reach out and say, hey, I'm interested in doing this kind of unique thing. What do you think about this? And so that's an option there. You can use this button right here. So another thing, there's another API that rather than giving you, just a quick image, you can take a look at the short answers API, which gives you a, that one doesn't have a quick example here. But you get the idea that there's also there's a API for our various calculators that are built into Wolfram Alpha. So Wolfram Alpha has a lot of handy calculators for various engineering and science course applications. And so if you want to be able to have an API just for those, there's one which is built to sort of be more for that use case. So that's the idea, is that there's the quick and simple, just give me the image of what your page would show. And then there's these other things which are out there for being able to, do a particular use case. So again, not quite what we were, focusing on for the original presentation, but since there's a question about it, might as well give a sneak preview.
Now, as we're coming to the end of our time, I'd like to address the elephant in the room. The question of, is this tool, especially step-by-step solutions, going to be used to cheat? Now let's define terms for a moment here. Cheating in this context meaning using this tool without attribution, presenting the work that comes out of step-by-step solutions as your own work without saying, I used Wolfram Alpha, and this is what it told me. Or using this tool when it has been explicitly disallowed. Like, for example, if you're taking a no notes test. Is someone going to cheat with this tool? Yes, absolutely. We don't like that. That is not something that should be happening, but it's going to. It's going to. So why am I bringing this up? I'm bringing this up because I want to address that this tool is also a darn good tool to prevent people from cheating, partly because it is a great way to teach people these concepts. That's the number one thing that we like about it, but also because the answers that these programs are going to give to step-by-step solutions, at least at the time that I'm speaking, are consistent. Sure, every, or at least a lot of prompts could have 2 or 3 different ways of explaining things, but for every user, each of those 2 or 3 are going to be the same thing that they see. You understand? 3 different explanations, but every user will get those same 3 different explanations to the same prompt. So in the same sense that someone is going to use, say, Google to cheat, the mechanism of seeing whether or not someone is copying something verbatim off of these results is pretty simple. Look the results up. So it's definitely something that's useful to anyone who's trying to see whether or not that's happening as well.
And I also think a really good point to keep in mind whenever you're thinking about, a student exhibiting a behavior that you don't want to see in your classroom. So it's really important to think about why students do what they do.
Yeah.
And the immediate reason might not be the one that is most obvious, right? So it's important. In fact, there's a whole literature and sort of practice of trying to understand, what is a particular behavior accomplishing for that student as far as the student understands what's good for them, right? Mm-hmm. Because anytime that a student is sort of not engaging with an assignment, that could be, what we might call cheating, where someone is like looking off on a person's paper. It could just be plain not doing the assignment, right? So any time that a student is not engaging with an assigned sort of task, that is always really part of the same umbrella issue, which is that there's a mismatch between what the student thinks is good for their sort of well-being and learning and the framing of the original task, right? Because if we're able to sort of notice, oh, wait, a student has either just plain not engaged or done some other activity that we don't want them to do, like, use someone else's work and pretend that it was theirs. That is an example of the framing of the thing not being such that the student says, yes, this is absolutely what I want to, have my time and energy spent on right now. And that in some cases that might not, what the student's own sense of what they have the time and bandwidth to handle might not be entirely under the student's control, right? Like I've taught in various contexts where, for reasons that were totally beyond the student's control, they just don't have the ability to do homework after they leave the school building, right? So I mean, these sorts of educational contexts exists where there's situations where the students have a lot of things that are happening that are not necessarily under their control. And so as an educator, you always have to sort of understand these larger contexts and figure out, okay, what's the thing that's going to help move this particular student forward and what's going to be best for their education in dialogue with, importantly, the student and the student's family and all the stakeholders. This is what makes education complicated, is that there's always a lot of stakeholders. So in brief, anytime the student through their actions is not engaging with, a particular thing, think about, okay, is that framed in such a way that the student really buys in that, yes, this is a task that is important to me. And then whenever you have that buy-in, a lot of the behavioral issues are just going to evaporate, right? And it's also worth saying that, students, like all of us, don't necessarily always have 100% sensible view of how things are going to impact them in terms of what's good for them and not good for them.
That's true. Might be thinking short term rather than long term, for example.
Yeah. And so again, as an educator, this is place where it's important to recognize when you think a student might be doing that, and to sort of point out, there's these skills that you develop as you go along where you're able to better balance short-term versus long-term. You're better able to sort of plan how these sort of things that you don't quite see how are fitting together into a larger narrative of how you're going to develop your skills to accomplish what you want to accomplish, right? And so by framing things in the way that is going to allow the student to really understand and feel, oh yes, this is an activity that I see how it's helping my learning, a lot of the sort of behavioral issues are going to not be present, right? And so that's not always an easy thing to do, but it's my go-to advice whenever there's a student behavior that is not what you want to be seeing in a classroom.
I also want to highlight something else that you were talking about earlier, which is doing a classroom activity where you take the various step-by-step explanations and ask people, what do you think of these explanations? Can you think of another way to do this? Is this similar to how you've done it? Can you think of a better way? Which of these is your favorite and why? Mm-hmm. And I love that, in part because it makes it harder to do any sort of cheating in that situation, because of course the tool is now part of the conversation and the tool can't tell you itself which is your favorite. You're going to have to be giving input on that yourself, but also because it hits at the main goal of education, debatably, the main goal of education, to do more than you could before. That's why we're in a class, to learn how to do something or understand something or attempt something that we couldn't before. And what we can do is based on our knowledge and skills, but also on our tools. We need to learn to surpass all of it, any of them. This is not a tool designed to do the work for you. It's a tool that will let us do higher level, more in-depth, more valuable work. And I just love it for that.
Yeah, and we as Noah was saying, we always want to build a higher order skill whenever there's a tool available that can help with any particular thing. The thing that is really handy to do in that situation is figure out, okay, how can what I was already able to do with this skill combine with what this tool is able to do in order to build an even higher order skill that lets me solve more problems, right? And that's just a handy thing to do in general. We had a question in chat that was quite interesting. So, can something like this help me learn topology, for example? So let me share my screen because there's a couple of things. Let me make sure the screen share works properly. So if I evaluate this, I just say topology right here. So what I did was in Wolfram Alpha Notebook Edition, typed in topology, and I hit enter. So can you see this other notebook that popped up on your screens?
Yep.
So what we got was applications and sort of concepts in topology that just show up right now. Another thing that we can do is I didn't actually draw attention to this because I wanted to be conscious of the time, but in a previous example, if we go up here when we were talking about kurtosis, right? So this is again something that you might want to touch on in a statistics class. But if you're not in a statistics class, maybe this is just an exploratory thing for your students. So aside just from asking for definition, one thing that you can frequently do is if there's something that is a term, you'll notice this is linked to Math World. So if I ask for the properties of this term kurtosis that's in here, I get this list of stuff. So I see that there's definitions, but then there's also this really cool URL. So I'm not sure if this will continue to show. Can you see Math World now on your screens?
No, you're going to have to share that separately.
So that popped up in my browser window. Just a second. So if you go to Math World, this is a really cool resource for learning all sorts of stuff. And you'll see here there's a whole thing on topology.
Also run by Wolfram, by the way.
Yeah. So and this Math World is just a free resource that's out there for people who are looking to learn stuff. So many of the definitions and things that are accessible through Wolfram Alpha are also just on Math World. And so you can
come from there.
Yeah. And so, you see that the tools are integrated in many ways. And so, this was the example that was in that notebook we were looking at earlier today. But if you're interested in topology, there's all sorts of cool stuff. So let's say you want to learn about fiber bundles, right? So this is a advanced topic that is actually really important for doing physics. But let's say that you're looking for a resource of learning about fiber bundles. Notice that it starts out with a really cool visualization. I think visualization is one of the things that really helps me learn the best. And so if you are like me in that, finding good ways to visualize stuff, look no further, right? So so that was one part of the question that I wanted to first touch on was, can you learn topology using things like this? And the answer is yes, there are ways to deal with topology in tools like this. Now, the other question is, will computer-assisted tools fully replace instructors? I think that's an interesting question. So if I go back to thinking about Vygotsky, right? So Vygotsky's main sort of contribution to the constructivist theory of education is this social dimension to things that we learn. There are some who would claim, I'm not sure I necessarily agree, but there are some who would claim that you need social interaction to have learning, that learning literally cannot happen without social interaction. That might be a slightly stronger version of the statement than I would subscribe to myself, but it's a very subtle philosophical question.
It could depend partly on how broadly you define social interaction. By some definitions, all communication is part of social interaction, and almost all learning happens when someone gives you some information, either through structuring an activity or giving you a book which has information written in it.
Right. So these artifacts that come from other people, depending on how you sort of philosophically interpret various things, you could say, oh, okay, so this book or this web page that was written by people is my social interaction for learning this thing, right? And so again, these are very interesting philosophical questions that you can read about sort of for their own sake. But in terms of will computers fully replace instructors? Again, we talked a little bit about this in our interview with Colin Chapman as well. This question came up. And I think the best way forward is going to be having humans in the loop, right? That's my sort of current opinion about a question like that, is that for various reasons, it's really nice to be able to deploy tools, because tools help us do things more efficiently and better is the goal of a tool.
Oh, yeah.
But having a human in the loop, sort of using that sort of art and skill that comes with experience, that, okay, maybe we have computerized tools that can do X, Y, and Z, but W is what puts them all together and figures out this is the best way to use this right now, right? I think having an instructor, or if you're a self-learner, I also am very much oriented towards self-learning. It's nice to be able to bounce your ideas off of other people and sort of have ways to compare your understanding with other people's understanding, right? Because the other thing worth mentioning about constructivism is that aside from people that emphasize the social aspect, there's also people that really emphasize the internal model aspect. And so, it's often the case that if you take two people who are incredibly knowledgeable about a subject, in fact, I don't remember it offhand, but I think there's a Feynman quote even about how remarkably little in common various physicists' explanations and understandings of the same thing are. This comes about because we're taking our prior experience and the prior thoughts that we've had, we're comparing that with new things that are coming our way, and out of that, we're sort of building as we go this idea of, how does something work? And so on the one hand, all your learning is going to be this kind of internal model of how you think stuff works. But the social aspect can also be important to sort of see, well, what do other people convey that they understand about this that I can try to incorporate into my own model? So that's a really interesting chat question.
Yeah, I remember the statement, anyone who thinks one book has all the answers hasn't read enough books. And what you're talking about here, John, saying that the internal perspective on learning on a topic is extremely important. reveals that the tools we're talking about here are going to be incredibly useful, but it's worth remembering that although they can give varied perspectives, they give limited perspectives. They give a particular perspective on a lot of topics, a reliably accurate one, a reliably useful one. But if you want to find out beyond that, you're going to need to start talking to other people or reading other books or looking at other websites. That the question of, can I learn about topology through these tools? Yes, absolutely. Absolutely. There is going to be a whole lot of information that you can get on any given topic from Wolfram Alpha, and it will be extremely helpful. But will it replace everything that a classroom will give you? It's pretty much impossible for any one resource to do that. Part of what a classroom gives you is a variety of points of view.
Mm-hmm. Yeah, this is a really important point.
Well,
yeah, go ahead.
I think I myself am running a little bit low on time, so.
Yeah. So one other thing I want to show here, then we'll quickly take a look at if there's anything else in chat. So I mentioned before, there's these blogs out here, if you haven't gotten a chance to take a look at them yet. So what's ChatGPT doing and why does it work? So this is a nice educational piece that talks about how one goes about, constructing text out of these models that GPT-2. I always prefix chat now because that's the way that everyone refers to the latest and greatest new transformer model. But so my verbal slip aside, GPT-2 actually is something that you can play around with through the Wolfram Neural Net repository. And so this blog post not only explains just in general some of the things about how these work, it also has, so these things are click to copy. So if you click here and then go into a notebook and paste what you get, it shows you the code that would generate these various things that are click to copy. So that's a cool thing that you can do. There's a particular image that I'm scrolling for. Yeah, so this is a very, very small neural net. So I forget the numbers of parameters that are in something like ChatGPT. I think it's in the high billions. I don't remember exactly offhand, but it's a very large number of parameters. But as with anything, if you're starting out learning something, it can be nice to see what does a small little example look like. So this is a picture that sort of shows the inner workings of a neural net that is 2 input. So 2 input might be an X and Y, and 1 output. So 1 output from 2 inputs is a function of X and Y that returns, let's say, a number, right? So you can take a step function like this that sort of has 3 regions, and you can train the weights and biases, and then inside each of these nodes, there's a nonlinear function. These nonlinear functions are the secret sauce of neural nets, because if you don't have nonlinear functions, you're basically just doing a bunch of matrix multiplication. But once you put in the sort of nonlinear functions that do their thing at each of these nodes, this allows a lot more behavior than just doing matrix multiplication. But the nice part about neural nets is that when you're training them, a lot of the training process also comes down to multiplying giant matrices. And so you can represent the weights of how well connected each of these neurons are to each other by numbers, arrange them into matrices. And so anyway, I don't want to get into too much detail since we've had a fairly long stream on the original topic. But if you're curious about any of this stuff, do check out this blog post that let me make sure that this winds up in the chat. That might take just a second here, but
very useful blog post by Stephen Wolfram. He's the author of the post and also the author of the Wolfram language, the code that underlies Mathematica and was the flagship product of all of this.
So let's see. Any other chat questions you have? We will be wrapping up after not too much longer, so make sure you get them in there if you're still tuned in and have questions. Yes. So
Yes.
one thing I really want to highlight is that, having a human in the loop, I think, is really handy for education. However, as an instructor, you can't always come up with arbitrarily many examples and have them at the ready to show your students whenever a student has a particular example about some problem they might not even encountered in your class, right? They come to you and they say, I'm struggling with this problem. How do I do it, right? So assuming that the stars align, you can sit down with a student and sort of explain in the way that you are paying attention to all the details and things like this. But other times this conversation happens like between classes in a hallway during a passing period where you're both late to the next thing. And yeah, so there's all sorts of things that can prevent a human from being able to sort of sit down and give the detailed explanation at the time that the student immediately has the question. This is another area where having a tool can be super, super helpful, right? So being able to say, okay, this is a type of problem that I can use these explanations that are generated in order to answer my first couple of questions I have about this, and then go check in with the human in the loop to get them clarified and solidify that knowledge, I think is a really good application of all this. So we have another interesting question. I'm not sure what happens if we ask what is the meaning of life, the universe, and everything.
Of course, we all know what the answer to that is.
Right. If you're.
Oh yeah. Let me just ask it that. Hang on. I'm going to share my screen for a second. So here we go. Full disclosure, I'm not flying blind. I know what it's going to say.
I actually didn't know what this one was going to say, although I had a pretty good idea.
Answer to the ultimate question of life, the universe, and everything. 42.
According, of course, to the book The Hitchhiker's Guide to the Galaxy.
Which has not steered me wrong yet.
So indeed, yes, Wolfram Alpha does have that one covered.
Yep. But much like in the actual book and or radio drama, film, however you ran into it, The Hitchhiker's Guide to the Galaxy, the answer in and of itself is not enough. In that particular situation, the answer was given, but it was pointed out that they didn't actually know what question it was answering. They knew it was the ultimate question of life, the universe, and everything, but that's not a question. That's a description of the question. So that's been pretty much the theme of the entire presentation here. If you want to get an answer, this is a good tool for that. If you want to go beyond the answer, not just what, but why, also that there are tools within this to help you do that. So glad we got a chance to show them to you today. Just going to check real quick, see if there were any last minute.
While Noah's checking the chat, another thing to mention is that we have some more interview live streams coming up. We have some chemistry related live streams. So let's say that you are really curious. Okay, I've seen that, yes, there are some chemistry show steps examples. I've seen some various examples of chemistry related stuff, in some of these other streams introducing what can Wolfram Alpha Notebook Edition do. I see that there's chemistry examples on the Wolfram Alpha page. I want to know more about chemistry. We have some chemistry themed things coming up. Also make sure to stay tuned for more information about APIs, and definitely check out blog posts related to both thermodynamics and machine learning. And there's a whole bunch of just other topics that you can find blog posts and writings about as well. It's a good place to browse if you're looking for interesting things to read. All right. So I'm not seeing any new chat questions at the moment on my end.
Someone just said that they did not get to see the answer to life, the universe, and everything. I can show in one more time in Wolfram Alpha Notebook Edition what exactly that is.
Also remember with Wolfram Alpha, you can just go that and try that yourself, right? Because Wolfram Alpha, just being a website that's out there, you know, you don't necessarily need to be signed in to get all kinds of cool results. I was not signed in when I was, answering that question earlier. So,
I want to just say to everybody on the chat, thank you for joining us today. Very glad that we could be with you. But also wanted to add, this is an interesting thing. Part of the lore of Hitchhiker's Guide to the Galaxy, which introduced this funny answer of 42 to the answer to the ultimate question of life, the universe, and everything, was to say that if the question and answer were ever both known in the same universe at the same time, that the universe would then cease to exist and be replaced with something even more bizarrely incomprehensible. Side note, there is also a theory stating that this has already happened. But anyway, just curious, what happens if I
show steps for
the
I've never tried this.
Question
Let's see.
of life, the universe, and everything. And then just gonna give this a try. Living dangerously. Well.
That one does not have show steps implemented yet, which is perhaps for the best, as Noah was saying, according to the novel.
But in any case, thank you again very much for joining us, and look forward to having you here for the next one.
Take care, everyone.